title of this episode is Choosing the Right Inferential Statistics Part 1, Test of Comparisons and Regressions. For many researchers, knowing which statistics method to use for analyzing a particular set of data is a daunting task. In this lecture, we will be focusing on the guidelines to choosing the most commonly reported statistics in literature. The objective of the lecture is to show you how you can choose the right statistics for the data you have at hand. Statistics is broadly divided into two, descriptive and inferential. Descriptive, as the name implies, merely describes the population. On the other hand, inferential statistics uses a random sample of data taken from a population to both describe and make inferences about the population. There are many ways by which inferential statistics can be grouped. This slide shows the scheme I have found most useful, but please note that this is by no means exclusive, and like I said, it is the scheme that I have found very useful to me. Basically, there are 5 main classes of inferential statistics. We have comparison tests, we have regressions, we have tests of associations, we have survivor analysis, and tests of agreement. Many people consider regression as tests of associations, the only difference being that they go further than the usual association statistics by looking for causality. Yet, some also regard regressions as a class of comparison tests. In this presentation, I am going to present a flowchart that considers logistic and linear regressions together with comparison tests in the decision-making process. I am doing this because, as I am going to show later on in the lecture, if you are familiar with the test of comparisons, then you have covered the most common statistics used in reported literature. By the time you add the two regressions to it, then you are mostly covered. I will be covering tests of association in a later lecture in the series. The steps to inferential statistics begin with the formulation of the research question, which will become the null hypothesis. The objectives are the measurable means to answer the research questions. Thereafter, you should decide on the statistics to use. And that is the aim of this lecture. Please note that the decision on the statistics to use should be taken before data is collected. The mistake that most beginners make is to collect the data and start deciding on which statistics to use after. That is wrong. You must always select the statistics to use based on the study design, which in turn is based on the objectives. The statistics in turn will determine the type of data that you will collect. Two conditions must be considered before you can select the broad class of statistics to use. The first condition is the scale of measurement, and this is broadly divided into numeric and categorical. The second condition that must be considered is the type of study design, which is either paired or unpaired. Let's take a closer look at the scale of measurement. It is broadly divided into numeric and categorical. A numeric variable can take any value within a range. Numeric data are further divided into discrete and continuous. Discrete variables can only be counted, they can't be measured. The Oxford Dictionary of English Language defines discrete as individually separate and distinct. Examples of things that are only counted but not measured are number of students in a class, heart rate, number of heads in 10 coin flips, etc. You are dealing with discrete numeric data if it cannot be divided into fractions. Continuous data can only be measured. They can't be counted. Therefore, they can be divided into fractions and can take decimals. Continuous data can be interval or ratio. Interval scales do not have a true zero. Example of interval scale is temperature measured on Celsius scale. Since they don't have a true zero, you can only add or subtract them. You cannot divide or multiply them. Ratio scales have true zeros. Examples include height, weight, length, etc. You can perform any arithmetic function with ratio scales. Categorical variables are quantitative variables that can be put in groups or categories. They can be further categorized as either nominal, ordinal, or dichotomous. Nominal variables are variables that have two or more categories, but they do not have any intrinsic order to them. Examples of nominal data include race and color. On the other hand, ordinal variables are variables that have two or more categories, just like nominal variables, but unlike nominal variables, the categories can also be ordered or ranked. Examples of ordinal variables include social status and Likert scales. Dichotomous variables are variables that can only take two categories. For example, yes and no, dead or alive, etc. Please note that the same data can be presented in different data formats. Take a person's height. It can be presented as a numeric data when it is simply measured in meters. However, the same person can be categorized into short or tall categories. Numeric data can easily be converted into categorical data, but the converse is not the case, as categorical data cannot be converted to numeric data without penalties. That is one reason why you should always collect your data as numeric if the option is available to you. After considering the type of data, the next thing to consider is whether the study is paired or unpaired. In a paired study, data is taken from the same participant on more than one occasions. The most common example is the before and after study designs. Matched pairs in case control studies are also taken as examples of paired data because even though the groups are different, values like age, sex, and weight in one group are matched or related to the same values in the other group. A crossover study design also calls for the application of paired group tests for comparing the effects of different interventions on the same subject. With independent or unpaired study, measurements are taken only once from each subject. In addition, the subjects are randomly selected from the population. In the case of numeric data, you must make a further distinction between whether the distribution of the data is normal or not normal. Normally distributed data should be analyzed using parametric methods, while non-normally distributed data can be analyzed using both parametric and non-parametric methods. This flowchart, while not comprehensive, provides you with the step-by-step guide to choosing the right statistics. It is provided with the following caveats in mind. First of all, only a few statistical methods account for most of the statistics from reported literature. The most commonly reported in medical literature are the student t-tests, contingency tables, which include chi-square and Fisher's exact test, ANOVA group, Wilcoxon and Mann-Whitney-U tests. If you should add correlations and regression to the blue, then you should have covered most of the statistical method you need as a researcher. Therefore, the first consideration is that we will be limiting the statistics on the flowchart to the most common statistics in use. Otherwise, it will be too cumbersome. In addition, we are not showing non-parametric techniques on the flowchart. This is because most of the commonly used parametric techniques have their non-parametric equivalents as shown on the table. For example, the non-parametric equivalent of the t-test is the Mann-Whitney-U. For ANOVA, there is Kruskal Wallis. For linear regression, we have non-parametric regressions as well as logistic regression. Peer-sampled t-test as Wilcoxon Rank test, and repeated measure ANOVA as Friedmann's test. So, if you have to know the requirements for a Mann-Whitney-U test, for example, just check out the requirements for the t-test and you are good to go. A special word on linear regression and logistic regression. For you to use logistic regression in place of multiple regression, you must dichotomize the outcome variable. Finally, we are not showing paired statistics on the flowchart. Again, most of the commonly used unpaired techniques have their paired equivalents as shown on the table. For example, the paired equivalent of the t-test is the paired t-test. The paired equivalent of ANOVA is the repeated measures ANOVA, and the paired equivalent of man with NIU is the Wilcoxon Rank test. And for Kruskal Wallis, we have the Friedmann's test. This is the first step of the flowchart. An inferential statistics must have at least two variables. One is the predictor or independent variable, while the other is the outcome or dependent variable. Your first consideration is the predictor variable. What type of variable is it? There are two possible scenarios. The predictor is categorical or it is continuous. Step 2a is where you should look at the answer to the question in step 2. Going further, we will first consider these possible scenarios on the left side of the flowchart, where the predictor variable is categorical. This is the side of the flowchart that is for comparison tests only. In step 3, if the outcome variable is categorical, then you should use chi-square. For chi-square test, both the outcome and predictor variables are categorical. Fisher's exact test is similar to chi-square test, and it is more accurate than the chi-square test in certain situations, such as when the expected value in a cell is less than 5. Such situations generally occur when you have small samples. Fisher's exact test is also limited to 2x2 tables most times. What if the outcome variable is continuous? Things are not as straightforward in that situation. First, you should consider the number of variables in the test you wish to do. The number of variables can be 2 or more than 2. For the 2-variable scenario, you have the options of either t-test or ANOVA. Your choice will depend on the number of groups in the categorical variable. The categorical variable can have 2 groups or more than 2 groups. When you have just 2 groups, your option is the t-test. In student t-test, the independent or predictor variable is dichotomous, while the dependent variable is continuous and normally distributed. Using the predictor variable as the basis, you should divide the outcome variable into groups and then compare the group means. For example, supposing you want to find out if there is a difference between the weights of boys and girls in a class. The predictor variable is gender, which has 2 categories, boy and girl. The outcome variable is weight. Therefore, you will have to compare the mean weight of boys taken as group 1 to the mean weight of girls taken as group 2. When you have 3 or more groups, you should use ANOVA. ANOVA is done when you have one independent variable with 3 or more categories and a continuous dependent variable that is normally distributed. So supposing you want to see if socioeconomic status has any effect on the weights of the school children we encountered earlier, socioeconomic status is your predicted variable, and it has 3 categories: high, middle, and low socioeconomic status. The outcome variable is weight, and since there are 3 groups, you will use ANOVA rather than t-test. To see what you should do when you have 3 or more variables in the proposed statistics, let's go back to step 3a. In that situation, your main options include MANOVA, ANCOVA, or the factorial ANOVA. Your choice will be based on whether the extra variables are outcome or predictor variables. When the outcomes are continuous and more than 1, you will use MANOVA. When the extra variables are predictors, your options will depend on whether all of them are categorical or they are a combination of continuous and categorical variables. When all the extra predictor variables are predictors, you opt for factorial ANOVA. On the other hand, when you have a combination of categorical and continuous predictor variables, as shown, then you opt for ANCOVA. For the regression arm of the flowchart, let's go back to step 2 again. But this time around, we shall be considering the right arm of the flowchart, which deals with the situation where the predictor variable is continuous. Let's go back to step 2a, where we will now consider the possible scenarios on the right side of the flowchart where the predictor variable is continuous. For categorical outcome variable, the recommended statistic method is logistic regression. For continuous outcome variable, you need to go a step further and consider the situation where you have one or more than one predictor variables. When you have just one predictor variable, linear regression is recommended. On the other hand, if you have two or more predictor variables, multiple regression is recommended. These 7 common statistics have been covered, and they are chi-square and Fisher's exact test, t-test, ANOVA, MANOVA, ANCOVA, logistic regression, linear and multiple regressions. The statistics listed on this slide have not been directly discussed. They are in 2 groups, non-parametric and paired tests. As discussed earlier, all of them have their equivalents in the parametric techniques. So therefore, in order to use any of these, just look at the indications for their parametric equivalents and you are good to go. We have come to the end of the lecture in which we have covered the important steps to choosing the right statistics for your research. I am Oluwadiya Kehinde, a professor of orthopedic and traumatology at the Ekiti State University at Ekiti in Ekiti State, Nigeria. I have been teaching SPSS in healthcare research since 2004 in Nigeria and South Africa. I'm also the author of the best-selling book on SPSS in Nigeria, Getting to Know SPSS. That book also contains supplementary chapters on Zotero, as well as how to search online for literature. I'm also the CEO of Post Educational Consult, which specializes in training in statistical software and health education. My website is at www.oluwadiya.com. Check it out for more information on my book. The website also contains close to 50 downloadable PDF copies of my lectures in anatomy and orthopedics. Finally, you will come across assorted information on medical practice in Nigeria on the website. Please subscribe to my YouTube channel at the address shown for other lectures in the series. The series also includes lectures in anatomy, SPSS, statistics, orthopedics, and traumatology. Thank you for your time and attention. And as they say in my language, ẹ ṣeun.